Alright, so in this lesson we're going to start taking a look at the pendulum. And the thing to point out about the pendulum is if we watch its motion here, we see that it looks an awful lot like simple harmonic motion. And in fact, it's usually one of the examples that I give for simple harmonic motion. But can we show mathematically that the motion of a pendulum mathematically looks similar to the motion of the spring mass system or any other simple harmonic motion? So let's look at the simple pendulum. And so the thing to point out about the simple pendulum is you usually have a large massive object connected to some point of rotation by a string or something that doesn't have much mass. We usually call this large massive object on the end a bob, just the technical name for that. And usually with a simple pendulum, we're going to pull it back angles so that this angle is relatively small. What starts to happen if you pull this back further is you start to introduce other types of motion in there that is not simple harmonic motion. So if we start to analyze the forces that act on the bob, we have weight and the tension in the cable, and here are the directions that those two forces go. The one thing we can say about tension in the cable is that it has to be bigger than the weight in this case because of that angle. We know the pendulum is going to be accelerating, and we know sum of all the forces equals ma. And we're going to assume the direction of that acceleration is to the right or toward this dashed line, which really is the vertical line from the axis of rotation up here. So we're really interested in this component of the force here. If we draw this out, it should be force of tension times the sine of theta. If we wanted to actually figure out what the tension is, we could say tension times cosine of theta equals mg. Solve out for the tension. We can substitute that in and get mg tangent of theta, because remember that sine over cosine is tangent. The one thing that's a useful approximation at this point is that since we've said that theta is small, the tangent of theta for small angles and theta are about the same value. And so I'm going to use that approximation. And we also know that acceleration is related to angular acceleration alpha, that angular acceleration times radius equals acceleration. And so really the radius in this case is going to be L. So if we plug that in, what we end up with is a relationship that looks like this. G over L times theta equals angular acceleration. Well, that's a function that has a second derivative and the function within it. That looks a lot like simple harmonic motion. There would be a negative sign in here. I haven't put the negative sign because as theta gets bigger, this acceleration gets more and more negative. It's in the opposite direction of theta. Since the angular acceleration is in this direction, theta is in the opposite direction. And we could also say that your omega value, your angular frequency is your angular frequency squared is g over L, which means we can get a function for the period that is related to L and G for the simple pendulum. Now what if we had what we'd call a physical pendulum? And what's different between a physical pendulum and a simple pendulum is in a physical pendulum you have mass spread out throughout the pendulum. So here I've taken, let's just say, a beam, put a nail through it on one end, and letting it swing back and forth like a pendulum. The way we could start to figure out what's going on here is I'm going to say the sum of torques on this object is equal to I times alpha. Well, the torque would be m times h times sine of theta. The main reason for that is your mh is this way, you have this way is your h, and the sine of theta would be this angle in here. You get a negative sign to flip the orientation in there. So if we plug that relationship in, that it's equal to I times alpha, we can do a simplification. Remember that for small thetas, sine of theta and theta are about the same. And if we rearrange this, we get that relationship there, which looks pretty much the same as simple harmonic motion. In this case, your angular frequency squared is mgh divided by the moment of inertia. And so your period is related to the moment of inertia and mgh. What h really is the distance between the center of mass and your axis of rotation. So let's use a physical pendulum to measure the constant g. And so if we wanted to measure the constant g, what we'd need to do is measure the period of a physical pendulum. This happens to be one of the most common ways to measure the constant g. Take something like a solid uniform beam, put a nail in it, and rotate it back and forth on the nail and measure the period. Some things we know about a solid beam is that if it's a uniform beam, the center of mass is located halfway down the beam, and if it's being rotated about the end of the beam, we know the moment of inertia is 1/3 ml squared. If we plug those two things into my equation here and do some simplification, we end up with that really G is only dependent on two things: the length of the beam and the period of its oscillation. So we go to try to solve for G. I'm going to square everything first, and I'll multiply everything by G and divide everything by period squared, and here we go. We have a relationship to calculate G from period and length of your physical pendulum. It happens to work out that you can do this yourself if you want to. If you create a physical pendulum using a uniform beam, you can measure the acceleration of gravity just by knowing the length and the period of its oscillation. So let's take a look at a problem where we have both a physical pendulum and a simple pendulum. And we're going to use a uniform meter stick pivoted about one end to create a physical pendulum. And I want to have a simple pendulum with a length L0 that has the same period. And I want to know what is the period of oscillation and the length of the simple pendulum. So the first thing we want to do is calculate the period of oscillation for my physical pendulum. The nice thing is, since it's a uniform meter stick, I know those two things are true. I also happen to know what L is in this case, that L is a meter. So if I plug those in, what we end up with is this relationship here, which we already did. And then if I plug in what I know about L and then the acceleration of gravity, I find that the period of oscillation of a meter stick about one end should be about 1.64 seconds. Now if I try to set up this relationship to calculate L0, the length of my simple pendulum, I could set the period of my physical pendulum equal to the period of my simple pendulum. First thing that looks like happens is the 2 pi's cancel out. I can square everything to get rid of the square roots. Looks like G gets to cancel out, and so really it's just 2/3 L, or 0.667 meters, or 66.7 centimeters. So that kind of quickly goes through the pendulum and some quick problem with the pendulum, and that ends our section on mechanics.